Okay. I think everything's okay. Hopefully my voice quality is also good. Great. Hello everyone and welcome to ML Done. This is one spontaneous live session. In particular, I'd like to talk to you about a concept that I've been studying about only recently called predictive coding. The way I understand it is that it's kind of a model, like a neural network, a model of the biological neural nets within our brain that is capable of making predictions. And the whole idea is that this model assumes that our brain keeps, making predictions about the world, about the sensory input, and once the actual values for those sensory inputs have been received, only then the network would basically compare the prediction and the actual sensory inputs and compute some error, and then that error is used to update the parameters of the model, aka the synaptic weights. There are two main differences compared to predictive, if you want to compare predictive coding with traditional artificial neural nets that are trained using backpropagation, that I'd like to point out here. Number one is when you want to train a predictive coding network where we have an input, it can be an image, and the output could be a class that image belongs to, like predict the class. This is basically a traditional classification task. Funny enough, there are two stages of training a predictive coding network. And funny enough, the first stage is, I'm not sure whether you're going to believe this, but the first stage is actually a backward phase, meaning that each layer within the predictive coding network tries to make a prediction of the neural activations of the previous layer or the layer below it. So deeper layers constantly make predictions about the activations of more shallow layers, and in particular, each layer makes a prediction of the immediate previous layer's activations, right? And then, after these predictions have been made, the actual value of those of the activations of those lower layers are compared with the predictions that are received from the backward pass of the layers above. And by comparing the predictions and the actual values, an error is computed. There are different ways of doing that subtraction, doing that difference between the ground truth and the actual the predicted activations. But regardless of that, the result of the backward phase is a bunch of errors. Like for each layer, you'll end up with an error, basically. And the second phase of the training is called forward pass. Right? This is where the computed errors are forward propagated through the network to update the parameters of the model, aka the weights. You could think about them as the weights. So this will happen until each layer becomes an expert in predicting the activations of the previous layer. That's how it works. Now, you can see that the main difference between training a predictive coding network and a traditional deep learning neural network, the main difference is that if you have a traditional artificial neural network and you'd like to train it, usually what you do is you have a forward pass that the input data goes through all of the layers. The final output is a prediction. The prediction is compared with the ground truth vector. An error is computed, and then this error is backpropagated throughout the entire network to update the parameters, with the hopes that once a new data is coming in, the next prediction would be better, right? But in predictive coding network, input data comes in, right? Each layer makes a prediction of the activations of the previous layer. Remember, the activations, the actual activations, which are the outputs of a layer of neurons. After each layer makes a prediction of the activations of the previous layer, basically the backward pass is completed, and then during the forward pass, these errors are computed, well, not computed, but forward propagated, so that the synaptic weights between the layers would be updated. So these are the two main differences. There is one other difference in terms of computing the error that I find fascinating. It's really amazing. If you think about the error functions that we use in artificial neural networks in deep learning, if you're doing, say, multi-class classification or one-class classification, regression, binary classification, time series forecast, whatever have you, in general, what you have is one global loss function, aka error function, that dictates the change in the entire set of weights that you have in your neural network. Namely, in order for you to be able to update a given parameter, everything else will be affected. So you've got one error function, you compute the gradient of that one error function with respect to all of the weights in your parameters. Yeah? But it has been argued that that is not how the brain is trained. That's not how it works in the brain. Namely, they say that the brain doesn't do backpropagation. In other words, the types of networks that are like predictive coding networks are very, very similar to how the brain is trained. The loss function, I told you about computing error in each layer, right? I talked to you about that. You can compute, or let's say you can formulate a loss function that can measure the difference between the activations of the layer below and the actual activations. So that loss function can be formulated in different ways. But the key thing is, the loss functions are defined purely locally. That's the beautiful thing about predictive coding. Sorry, I have to keep moving so that the sensors would keep the lights on. That is the main difference between traditional deep learning approaches to predictive coding approaches, where with predictive coding you define a local loss function, meaning that if you have neuron A and neuron B and there's an edge between the two with a weight, all you need to know to be able to update the value of this weight is literally the presynaptic activation, the postsynaptic activation, and that's it. So you don't need to know anything else about any other part of the network. That's the amazing part of this. So it makes it much, much easier to train these models. So by defining these local loss functions, you're making the task of updating parameters gets broken down into many local updates, right? They call these like Hebbian update rules because they're fully local and they're purely depend on the presynaptic and postsynaptic neurons at the end of a given connection, right? The last point that I'd like to make here is, I told you about the fact that in a predictive coding network, a given layer, makes a prediction of the activations of the previous layer. That's great, right? We talked about that. But I'd like to make a point in terms of how that prediction is happening exactly. Like, how can you make that prediction? What does it even mean for a layer to predict the activations of the previous layer? One very, very popular approach to do so is a Bayesian approach, or Bayesian approach. Meaning that, given the observation that I have, like let's say I'm layer number 3, given the signals that I've received from layer number 2, that is my observation, let me compute the posterior probability of a hidden variable that is the activations of layer number 2. So given an observation, excuse me, given an observation, let's compute the hidden variable that is the activations of the previous or the layer below me. And because that posterior probability, if you're familiar with Bayes' rule, the posterior probability in general in a real life situation is intractable to be computed exactly. And there are different methods that you can approximate this posterior probability. Namely, you've got, for example, Monte Carlo, sampling. But my favorite approach is variational inference, or VI. That's how they denote it. Using variational inference, you can actually approximate the posterior probability. Again, let me be clear what I mean by posterior probability. It means layer number 3, for example, looks at what it has received from layer number 2, so the observation from layer number 2, looks at it, and then answers this question. Like, what is the most likely hidden cause in layer 2 that has resulted in my current observation? So because this prediction is happening after having observed the signal from layer 2, that is why it's called posterior probability. It means posterior, after having observed the data from layer below. But by estimating, let's say, by estimating the posterior probability, you find a vector of activations, or let's say you predict a vector of activations in layer below, which maximizes the posterior probability for the activations for the layer below. Right, so in other words, you're computing the most likely activation vector for the layer below. So that is one approach of making predictions about about the activations of the layer below. And there are all sorts of approaches to do so. And as I said, variational inference is one thing. Now, if you are curious about predictive coding and you wanted to take a deeper look, you might also hear about, during variational inference, you might hear about minimizing free energy or maximizing evidence lower bound. So these two concepts are nearly identical. And what it means is, by minimizing your free energy, which is just a fancy way of describing a mathematical formula. By minimizing that sort of quantity, you are becoming better and better in estimating the posterior probability of the hidden variable. It's exactly the same as maximizing the evidence lower bound. And so they're absolutely identical. So if you heard these terms, yeah, of course you need to, if you're not familiar with them, you need to go and read about them. But I just want to let you know that these are just fancy ways of saying that we have this sort of objective function that we can minimize, or this other function that we can maximize, and the result of both optimizations, either 1 or 2, whichever you choose, is nothing but becoming better and better in estimating a posterior probability. Now, the last point that I'd like to make is that the neural networks that are named predictive coding networks, the reason they're called predictive coding is that there are two types of neurons in a predictive coding network. One is the neurons that make predictions about the neurons about the activations of the neurons in the layer below, and the other family of neurons are the error neurons. So these are the neurons that encode or code the difference between the predicted activations and the actual activations. So because they sort of encode the difference or like the difference between the two, between the activation and ground truth. So they're sort of called, I think that is why it's called predictive coding, because they code the difference between a prediction and the actual value. I think that's why it's called predictive coding. Now, what should you read if you're interested in this area? I would recommend a paper, a tutorial for energy-based, what was it? Energy-based, a tutorial on energy-based frameworks for modeling perception, something like that, by Rafael Bogaz. Rafael is R-A-F-A-L, Bogaz is B-O-G-A-C-Z, I think, yeah, from Oxford University. He's the main author of the paper. And he has written this tutorial that goes from, starts from the very, very basics of predictive coding networks and describes everything. And it's amazing. That's a beautiful, beautiful tutorial. The math looks intimidating, but trust me, it looks intimidating, but it's not that difficult, really. So I would recommend that paper for sure. And last but not least, predictive coding networks originally were prescribed to sort of model the visual cortex in our brain, the way different layers of biological neurons in our visual cortex interact with one another across different layers to make sense of the actual object that is in front of our eyes. So given the light intensity that I'm observing right now through my visual, through my eyes, what is the most likely, let's say, object that is in front of me right now? Right? So this is called perception. So predictive coding networks were originally proposed to model human perception. Given an observation, figure out the hidden variable that is most likely to be the cause of the current observation. Now, later on, Professor Carl Friston from University College London made a few, let's say, improvements on this model. I would say maybe improvements. I'm not sure whether that's the right word, or I suppose it is. Professor Friston actually encoded a measurement for uncertainty in those predictions as well into the model. So these uncertainties could actually be tuned during the learning process of a predictive coding network. Originally, uncertainty wasn't a learnable parameter in these networks. So Professor Carl Friston, he added the learnability, or so let's say a learnable parameter that describes the uncertainty of the predictions as well, so that could also be tuned, right? And later on, he added a major thing on top of a predictive coding network, meaning that with a predictive coding sort of model, you can already model perception, right? However, Professor Friston also added the decision making on top of a predictive coding network, where you as an agent in your world can not only perceive your world, but also you can choose actions, right? So you can define a sequence of actions and choose to commit to a particular sequence of actions that would be rewarding for you in some sense. So the addition of action selection or policy selection to a predictive coding setting resulted in another model that is called active inference. It means you're actively inferring the best sequence of actions. Namely, in order to perceive, or let's say make a perceive the world around you, the quantity that you're using, or let's say the quantity that you're minimizing, is called free energy, or more accurately, it's called variational free energy, or VFE, right? and the quantity that you need to minimize to find the best sequence of actions, because you have to look into the future, right? It's about what should I do in the next few time steps to achieve something. Because it's about the future, a future that hasn't yet come, the quantity that you'll be minimizing is not variational free energy, but it's expected free energy. That tweaks the math a little bit, but I mean it makes sense. And there is a paper on active inference. I'm not. It's sort of. I think the title goes along the lines of a step-by-step tutorial on active inference, something like that. Very, very close. Professor Carl Friston is one of the authors as well as two other students. I think at the time there were PhD students. I think one from the U.S. And the other one I think from Cambridge. So in that paper, it's again a tutorial. They go through everything, and I mean everything, the entire math. All of the derivations are there. There's code available for simulating an agent that uses active inference and a variation of free energy to both perceive the world around it as well as make decisions about the world. So that again is an amazing paper if you want to learn about active inference. I would say the most interesting thing about learning about these ideas is that it motivates multidisciplinary research. Like if you are, for example, a machine learning expert, like myself, I'm a machine learning guy. Learning about these mathematical modeling, dimensions, in terms of modeling the brain, the decision-making process of the brain, as well as modeling the perception within the brain, would really complement your machine learning sets like really, really interestingly, really well. So you can develop deep learning models that are motivated by a biological neural network, namely the brain that we have, right? There are papers out there which have actually, simulated a predictive coding neural net that does image classification, time series prediction, and they've shown that they beat the hell out of traditional backpropagation in deep learning. And it's just amazing. And there are papers out there. There's one particular paper that shows that a local sort of loss function that you describe in a predictive coding network, the gradient of this local loss function with respect to the learnable parameter, let's say the weight, they've shown that this approximate the actual, like the deep learning based, gradient computation, the actual gradient of say the global loss function with respect to that local parameter. It actually approximates that global gradient really, really closely, even though that's a local measure. So it's very, very interesting. So I strongly recommend anyone who's out there who's interested in predictive coding, in particular, if you're a machine learning guy, I strongly recommend you to take a look at this area. And who knows, maybe this becomes your new area of interest, and you'll be more interested in working towards this area. There are many well-known universities that have research groups that are actively working in this area. I've seen a lot of projects in Oxford University, Cambridge, King's College, and also lately I've sort of came across a research group at Monash University in Australia. So they are working in this area. It falls under, what was it? The math of psychology, or computational psychology. Very, very interesting areas. So I'd like to also mention that using these mathematical models, you can actually model different mental disorders. Like you can actually model a patient who is suffering from schizophrenia or Parkinson's disease, or whatever mental disorder that is out there. You can actually model these diseases mathematically. And once you do that, you can actually, de- develop neural networks that are sort of modeling a sick patient, a patient who's suffering from a particular mental disorder, and you can try and fix this issue, or let's say cure your artificial patient by making different adjustments in different parts of the network. So this could help you with coming up with different strategies for curing different patients with different types of mental disorders. So there are, I think, innumerous applications in healthcare as well. Now, I myself, I'm new to this area. I've just started learning about it, and quite frankly, I've become fascinated by it. So there's a very good chance that the paper reading sessions that we will have on MLDON, hopefully soon, I think is going to start with these topics like free energy principle, or active inference, or predictive coding, and so on and so forth, because I'd like to spread the word, especially to the machine learning community, because at least here in our university, or even in Ireland in general, I haven't seen any multidisciplinary research group who are working in this area. So I'd like to play a small role here and spread the word, so that more people would, especially in the machine learning community, would become more familiar with this area, and maybe tickle some curiosity out there, so that people would maybe start doing serious research in this area in the machine learning community. And I mean, this motivates multidisciplinary research, that I think is the key component for a successful research project at the end of the day, especially nowadays. Anyway, I hope that this was useful for you, and take good care of yourself. Bye.